Newton's second law, which first appeared in his masterpiece Principia, suggests that force applied on a particle is proportional to the change in momentum. That is, force is equal to mass into acceleration relation. Here, for a given force, more acceleration will be caused to a lesser mass and less acceleration for a higher mass. When the similar law or the similar equation is extrapolated to rotation of a body, the equation changes to tau, that is torque applied on a rotating body, is equal to I, that is moment of inertia, into alpha, that is its angular acceleration. Here, in the similar manner, the moment of inertia of the rotating body determines its angular acceleration when a given torque is applied. Hence, we can say moment of inertia is a equivalent of mass in case of rotation of bodies. For a point object that is rotating from a given axis at a distance of r, the moment of inertia is defined by the formula I is equal to mr square. Here from the equation itself we can understand that it is proportional to the square of the radius, that is when radius changes, the change in moment of inertia is more than when mass changes. In the real life, we won't be dealing with much of the point objects, we will be dealing with big bodies, that is big objects like a ring, like a disc, etc. For that, this simple equation of I is equal to mr square has to be extended to the different bodies by the method of integration in mathematics. For instance, we can derive the equation of moment of inertia for a rod which is rotating about its midpoint along perpendicular axis. Here we will consider L as the length of the rod. It has other dimensions negligible. We also consider that the mass is distributed evenly in the rod and the mass density is m divided by L. We can just get the mass of a given length of the rod by just multiplying by this density, that is m divided by L. Now we consider a particular small distance dx from a distance x from the axis. The moment of inertia for the small strip will be m or del m, that is a very small mass, into x square, as we have seen in our first equation, that the basic equation of moment of inertia. We can get the mass of the dx strip by just multiplying it with the density, that is m divided by L, and hence we have del m is equal to m divided by L dx. So a small moment of inertia, that is del I, for this particular strip will be equal to m divided by L into x square dx. On integrating from minus L by 2 to plus L by 2, as we have origin in the axis, we get moment of inertia of this total body, and this will come out to be ml square by 12, and the detailed integration of this will be given in the description box below. Similarly, we can find moment of inertia for different orientation of different objects such as sphere, disc, cube, etc., and can be used in different rotational calculations. Hence, we conclude this presentation on moment of inertia. Thank you all, and this is Dreaming to be Educator signing out. Thank you.